Here we have an example, a design example, where we want to design a synchronous BCD counter. We are going to use the sequential logic model to design the counter with D-type flip-flops. Over here you can see the state table. We have 4 flip-flops. You can see here the current state. So we can have 0, 0, 0, 0, and then the other values. And over here you can see the next state. So basically we want to count from 0 to 1, from 1 to 2, from 2 to 3, and so on and so forth. The last value will be equal to 1001, which stands for the decimal value of 9, and from that we will switch to 0. So basically this will be the this will be our state diagram from 0 to 1, and we don't have any input here. From 1 to 2, from 2 to 3, 4, 5, 6, 7, 8, 9, and then back to 0. For our state table, the input combinations 1, 0, 1, 0, 1, 0, 1, 1, up to 1, 1, 1, 1 are the don't care cases, because we don't expect those cases to happen. So now what we need to do is to find out the expression for the input of the flip-flops. Let me just draw the key map, the Carnot map. Here we have Q8, Q4, Q2, Q1, and I'm going to do it for the least significant bit first. So for Q1, the bit position of 1, Q1. If we fill it, we will have 1, 0, 1, 0, 1, 0, 1, 0, and 1, 0. And the rest are don't cares. Now we need to find out the expression for this. For Q1, I think the simplest case would be to consider these 8 min terms together, and that will give us not Q1. So Q1 at t plus 1 will be equal to not Q1. So it is quite simple. We can do it for the other inputs to the flip-flops as well. In a similar way, you just form the truth, you just form the key map and fill it, and then find out the expressions. If you do so, you can end up with these expressions that we have. D1 is Q1 at t plus 1 is indeed giving us D1. So this is the input to the flip-flop at the position 1. And for the rest, we have the expressions here. So you can practice finding out those expressions on your own as well. You can follow them to see how they are obtained. And then we can draw the logic diagram for according to these equations. We will have D Q1, D Q2, Q4, and Q8. Keep in mind that all of them will receive the same clock pulse because we have the synchronous BCD counter. So their content will be updated simultaneously. And then for the input of each flip-flop, we just refer to the expressions that we have obtained. For example, for the first one, we have D1 equal to not Q1. And then for the second one, for D2, we have Q2 XOR, so we need to use one XOR gate here. One input comes from Q2. The second input is Q1 and not Q8. So we need to use one AND gate where we have Q1 as one input and not Q8. I just use different colors in order to show you the connections. And we can do the same for the next ones. And we will have our synchronous BCD counter. We would need to have some synchronous or asynchronous reset as well. Some interesting thing here is that I already have shown you the state diagram that we are interested in with the don't care cases in the state table. But we also need to check out what happens if for any reason we end up at a state at the value which corresponds to the decimal value of 10, 11, or up to 15. Yeah? What happens? How our circuit is going to behave. To determine that, we can refer to the expressions that we have found for the input of the flip-flops or to our circuit diagram and determine what will be the next state when we have decimal value of 10, 11, 12, 13, 14, and 15. We just determine the next state by referring to the expressions and or to referring to the circuit diagram. And here you can see what will be the next state. Starting from 10, if we start at this state, in one clock pass we will go to 11, and in the next clock pass we will go to 6, and afterwards we will remain in the main loop. If we start by 13, in one clock pass we will go to 4. But if we start with 12, in one clock pass we will go to 13, and then in the next clock pass we will go back to 4. So you can see that if we start at any unwanted, let's say, state, it will take us at most 2 clock passes in order to go back into the main loop. So this is what happens when we consider all these cases as don't care cases. But if you want to have any specific behavior, for example, if we start by any of these unwanted states, only in one clock pass we can go back to 0 or to any other value. Yeah? In that case, you just fill the state table on your own based on your requirements, and then you will not have any don't care case, but you will have the full state table. Based on that, you can obtain the expressions for the Q1, Q2, Q3, and Q8 at the next rising edge of the clock. Yeah, or you can find the expressions for the input of the D-type flip-flops. The expressions that you get here will be different than the expressions that we have obtained, but the behavior of the circuit will be as you desire. So it will not be. It won't be similar to what we have here. Yeah. For example, as I mentioned, you can determine that if we are outside of the main loop, so here is our main loop, let's assume 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Starting from any of unwanted states such as 10, 11, 12, 13, 14, and 15. As an example, you can say that if I start from any of these, I would like to go back to 0. So what you need to do is that you come here, you just fill these with zeros, because your next state will be 0, 0, 0, 0. And then you have the updated state table. You just refer to that, fill the kernel map, and find out the expression for the input of the flip-flops. And then that will be your synchronous BCD counter as you wish.